Histology, if you remember, is the description of tissue. So we're going to go ahead and talk about bone tissue. Something to remember as we're discussing this, by the way, is that anything that says osteo on it refers to bone. O-S-T-E-O refers to bone. Bone contains lots and lots of bony extracellular matrix. Remember that it is a connective tissue. Connective tissues really do have more protein hanging out on the outside interconnecting it rather than having the cells right by each other so much. So this extracellular matrix that is made 15% water, 30% collagen. This is the 55% crystallized mineral salts love to hang out onto that collagen. That collagen is a protein. It's the starting point. It's where the osteons and the bone cells know where to build and how to build and where to deposit those crystallized mineral salts. And there are 4 different types of bone cells. Notice again that osteo is attached to every single one of them. Osteo refers to bone. We've got osteoprogenitor cells, osteoblasts, osteocytes, and osteoclasts. The osteoprogenitor cells are the ones that are responsible for forming all of the rest of them. Osteoprogenitor cells, if you want to build something, are going to differentiate or change into osteoblasts. If you need bone to get broken down and it's getting signaled, then osteoclasts are formed. Osteoblasts are having fun building. Blasts build. That's how I remembered it. The B starts with build. Clasts like to clash and break things down and plunder. Clasts clash and break things down. Now, something interesting about osteoblasts. They do build when they're signaled correctly. Bone and all that stuff, maybe even build it, but they also have a problem of painting themselves into corners. When they paint themselves into corners, they get stuck in that really strong bony matrix. They sort of go sedentary, but not too sedentary. They're there maintaining it. They're maintaining that bone matrix, kind of like the endosteum's there to help maintain the bone. Inside that compact bone, that spongy bone, you also have trapped osteoblasts, now called osteocytes, helping maintain that bone. In compact bone, I just realized that we were doing a second video, so I should definitely just quickly revisit compact bone. Compact bone is that thicker portion of the bone, the outer edge, that provides that really strong structural protection and support that you need. While the spongy bone adds that light weight, but still giving that pressure, that support that you're going to need. Let's go ahead and take a look at the compact bone really quick, the histology and the makeup of compact bone. You're going to notice these little, remember those progenitor cells and the osteoblasts, osteocytes? These things right here that are stuck in these little rings that looks like onion rings to me almost are the osteocytes. These osteocytes are all interconnected in some type of way through these concentric lamella. They look like little onion rings to me, and you'll notice that these onion rings are all circled around a very, very important supply, your blood supply, that has the ability to bring oxygen and nutrients while also hauling away waste products. Each one of these onions, if these are all layers of an onion, and a complete onion would be called an osteon. Again, it's a bone, it's osteon. Each one of these rings are called lamella, and they're concentric because they come one right after another. These closer osteocytes have a nice little, you're going to notice that there's some little faint lines in between all these different things. These lines are called canaliculi, and these osteocytes have fed little appendages through each one of these things to help interconnect the cells. Because if you didn't have these caniculi, if you didn't have these little sites, or these little exchange points, then these cells would die out here. One from food deprivation or the nutrient deprivation, but also from waste product buildup. So these cells are helping one another out. These guys are transporting oxygen and nutrients out and then allowing that the waste products such as CO2 and all that stuff to go back into that blood. Now, the hole that these blood vessels are in are called osteonic canals. Osteonic canals will interlace with one another because, again, if you remember that picture, that bone, that compact bone's all the way around. There isn't just some type of little itty-bitty holes, giant holes going through these things. You have only itty-bitty holes through. There's the endosteum, periosteum again, perdón. And how do you get blood to these deeper osteonic canals, also called Haversian canals? Well, you do it via the interosteonic canal, or Volkmann's, or perforating canal. Interosteonic, remember that the interstate is there to help bridge states, the United States together. So interosteonic is bridging osteons together. Something to note, whenever you get a cross-section of a bone, you'll see some of their osteons are complete, while some of the osteons aren't perfect little onions. That's because the bones are slowly remodifying over time. The older osteons are the ones that are less complete, while the newer osteons are the ones that are complete. And about every 20 years, you're going to have a new skeleton. Do want to point out one last thing. Notice that if you remember with connective tissues, the cartilages, that the places where their cells were hanging out were in lacuna. Look where these osteocytes are hanging out. They're hanging also out in lacuna. To really denote something that these, both the cartilage and the bone, have a very similar start. And we'll be talking about that here very shortly after we discuss ourselves a little bit about the spongy bone. You'll notice that spongy bone is kind of small, and because it's smaller in appearance, you don't really need that osteonic canal. All you really need is the lacuna and osteoblasts on the outside, osteocytes inside, with the occasional osteoclast. In between these trabeculae, or these holes and all this stuff, you're going to find red bone marrow. You're also going to find the capillaries and blood vessels necessary to feed these guys. And since these things don't go very deep, you don't really need that osteonic canal. You do need to note that you do have nutrient arteries and nutrient foramen. What that actually means is that there are some holes that introduce very, very large arteries and veins into that bone so you can actually feed that inner bone. You're going to have one going into the diaphysis, a couple into the metaphysis, and a couple into the epiphysis. How they originated and how they grow actually is indicative of how it began as a fetus, in the fetus. So if you remember a little bit, I'm going to go ahead and skip over to endochondral ossification. Endochondral ossification actually refers to the formation of long bone. Endochondral ossification, and there's a reason why. So first off, note that this little model right here at step 1, you have a cartilage model. You have somewhat of the bone formed, but it's not really looking like bone. You couldn't really take an x-ray of it and say, oh yes, this is bone. It's just cartilage. Cartilage doesn't show up so well on x-rays. Eventually though, you're going to notice that osteon, those osteocytes, are going to start forming. The osteoprogenitor cells are going to start taking over, and you're going to also note at this point of being taken over, you got a nutrient artery going in to feed. So there's got to be some type of relationship with blood invading finally and the formation of bone. Do we need to know it in this class or in any other class? No, not really. What that underlying thing is that induces the formation of bone. We do have, that's the first time. We do, however, need to note that this endochondral ossification, or the ossification of the long bone, is pretty darn neat, and it is induced by blood and whatever blood is carrying. And later on, as the diaphysis is forming, the epiphyseal arteries start forming as well. And the epiphyseal artery starts forming the head, and you'll notice, if you remember back from our histology or the basics of a long bone, that epiphyseal plate is forming, and that is where you're going to see growth occur here after the child is born. That growth plate, that's another word for an epiphyseal plate, is the growth plate. It's where the child's bones are going to grow. So that's long bone formation. It's the endochondral ossification, meaning that you get chondral, remember, means cartilage. So it's growing inside cartilage. It's ossifying inside cartilage. Flat bone is via intramembranous. Intramembranous kind of reminds me of a sandwich. This is why. You start off with a nice little patch of some osteoblasts working together to try and form an ossified tissue. Eventually, these things start forming kind of like a layer on either side of the bone, kind of like two pieces of bread sandwiching together the delicious ingredients of a sandwich. Eventually, this sandwich, this intramembranous, these are actually membranes, that's why it's called membranous, intramembranous, in between membranes, will eventually form that calcified bone, that flat bone. So flat bone is via intramembranous ossification. Well, long bones is via endochondral ossification. So continuing with the thought of endochondral ossification with long bones, if we're going to grow lengthwise, you'll notice again that epiphyseal plate. The epiphyseal plate in adults is completely solidified, but this is a picture of a child. You may remember me mentioning a little bit about how cartilage isn't very well viewed in x-rays. This is an x-ray of a child, about a 3-year-old's femur. You'll see that epiphyseal plate, epiphyseal plate is not very well seen. What's going on here? Here is the diaphysis right here. It's a little upside down to help you picture it. This is the diaphysis here. This is the bottom portion of that child's femur. You'll see that it's actually hyaline cartilage in this plate. And as this stuff divides and goes towards the ends, the epiphyseal ends, the stuff that is left behind begins to proliferate heavily. And as it gets further and further away, it begins to ossify. So that's how a long bone grows lengthwise. If you're talking width, though, well, those osteoblasts are doing a good job. They're building up that bone tissue. If they find an artery or a vein, both an artery and vein, they're going to envelop it. They're going to surround it and form that osteon. Again, those osteoblasts will begin to not accidentally, but intentionally paint themselves into corners and become nurturing cells, again called osteocytes. Eventually, the width will continue onward until you are formed into an adult. You'll see that infants start off nice, thin, and small, and then progressively get wider and wider to help support that larger and larger weight that's placed upon their bones. With that, let's do a quick thought exercise. Which femur, by the way, do you think is from an athlete? Well, obviously you're not here to answer my question, but you'll see that the one on the left is an athlete's bone and the one on the right is a normie's bone, like you and I. Why do you suppose that is? Okay, not going to waste any more time. Go ahead and pause it if you want to think about it. We're going to go ahead and talk about it now. When you are exercising, when you are putting effort and force onto a bone, that bone learns that it has certain weak points in those repetitive actions and activities. And as you do that, the repetitive motion will cause these bones to develop and adapt to those stresses. The more demand you put on those bones, safely, mind you, safely, please remember safely, the more and more those bones adapt and become stronger to deal with those stresses. Again, another push to go ahead and get up, get some exercise, get strong, and help yourself avoid getting breaks that you really don't want to have. Well, let's say that you do break your bone. Let's say that you do break your bone. How does it work? We're going to go ahead and discuss that in a little while in another video. Hope you have enjoyed this thus far.